Hello and welcome. Today, we're going to do something pretty ambitious. We're winding the clock all the way back, 13.8 billion years, to tell what might be the greatest story ever known, the story of our universe.
I mean, it's the ultimate question, right? Where did all of this come from? Well, the answer is a theory so profound and so incredibly well supported by evidence that it's literally the foundation of all modern cosmology. So let's dive in.
To really wrap our heads around this huge story, we're going to break it down into 5 parts. First, we'll tackle the main idea. Then, we'll look at the rock-solid evidence for it. After that, we'll walk through the timeline of creation, see what our universe is actually made of today, and we'll end on what is probably the biggest cliffhanger in all of science.
All right, first up, the big idea itself, cosmic expansion. And I'm telling you, getting this one concept right is the absolute key to understanding everything that follows. So here's the core of it. About 13.8 billion years ago, everything, and I mean everything, all matter, all energy, space and time itself, was crushed into a single point of unbelievable heat and density. And from that initial state, it started expanding and cooling. And that expansion is still happening right now.
Now, this right here is probably the most important thing to unlearn. The name Big Bang is kind of misleading. It makes you picture a bomb going off in some big, empty room, but that's not it at all. It wasn't an explosion in space. It was the expansion of space itself. Every single point in the universe began moving away from every other point, which means there's no center, no single point where it all started. It started everywhere. And these 2 classic analogies really help make that idea click. Okay, picture a loaf of raisin bread dough rising in the oven. The galaxies are the raisins. They aren't moving through the dough. The dough itself, that space, is expanding and carrying the raisins along for the ride. Or think about drawing dots on a balloon and then blowing it up. As the balloon inflates, every dot moves away from every other dot. No single dot is the center of the expansion. That's our universe.
So it's a really cool idea, but how do we know it's actually true? Well, the whole theory rests on 3 massive pillars of observational evidence.
The first pillar, believe it or not, didn't start with a telescope. It started with math. Back in 1927, a Belgian priest and astronomer named Georges Lemaître was looking at Einstein's equations of general relativity and had this radical thought. The equations implied that the universe itself had to be expanding. Then, just 2 years later, the astronomer Edwin Hubble provided the smoking gun. He was looking at distant galaxies and noticed that their light was stretched out, shifted towards the red end of the spectrum, a redshift. And here's the crucial part. He discovered that the farther away a galaxy was, the faster it was moving away from us. It was undeniable proof. The universe was expanding, just as Lemaître had predicted.
Okay, pillar number 2 is maybe the most incredible piece of evidence of all. It's the afterglow of creation itself, the cosmic microwave background. See, back in the 1940s, physicists predicted that if the universe started in this incredibly hot, dense state, then the leftover heat from that fireball should still be around, detectable today as a faint, uniform microwave energy filling all of space.
And in 1965, they found it, completely by accident. 2 radio astronomers, Penzias and Wilson, were trying to use this big radio antenna, and they kept picking up this persistent, annoying background hiss, this static. They couldn't get rid of it. They pointed the antenna everywhere, they rechecked their systems, they even cleaned out the pigeon droppings inside the antenna thinking that might be it. But that static, coming from every single direction in the sky, it wasn't noise. It was the echo of the Big Bang.
The third pillar confirms the hot part of the hot Big Bang model. The theory makes another very specific prediction. In the first few minutes, the entire universe was basically one giant nuclear fusion reactor.
And that cosmic reactor should have cooked up a very specific recipe of elements. By mass, the universe should be about 75% hydrogen and 25% helium. So astronomers went out and looked at the oldest, most pristine gas clouds in the universe, the stuff that hasn't been changed by stars, and what did they find? A perfect match. This agreement between prediction and observation is just overwhelming.
Okay, so we've got the evidence locked in. Now let's walk through the actual story, the timeline of the cosmos, from the very first instant until the very first stars blinked on.
It all happened so fast at the beginning. In the tiniest fraction of a second, a period called inflation blew the universe up from subatomic to gigantic, faster than the speed of light.
stretching out tiny quantum fluctuations that would one day become galaxies. Then, in the first 3 minutes, those first elements are forged. At 380,000 years, the universe finally cools enough to become transparent, releasing that ancient light we now see as the CMB. And then, darkness. For 400 million years, until gravity could finally pull enough gas together to light up the very first stars.
Just think about this. That 3-minute window was everything. It was the only time in history that the entire universe was hot and dense enough to act like the core of a star. It was a fusion-powered furnace that slammed protons and neutrons together to create hydrogen and helium. But then, because space was expanding so rapidly, it cooled down too fast for heavier elements to form, locking in that 75-25 ratio for all time.
So that ancient recipe, that hydrogen and helium, is what built all the first stars and galaxies. But here's the twist. It turns out that all of that stuff is only a tiny fraction of what the universe is actually made of today.
Just look at this. It's kind of staggering. All the stars, all the galaxies, all the planets, you, me, everything we've ever seen or touched or even conceived of makes up only 5% of the cosmos. The other 95% is a complete and total mystery, split between two things we've had to give placeholder names to: dark matter and dark energy.
So what are they? Well, we think dark matter is this invisible gravitational scaffolding. It's the extra mass that holds our galaxies together and stops them from flying apart. And dark energy? That's even weirder. It seems to be some kind of mysterious force, a property of space itself, that's causing the expansion of the universe to speed up.
And that accelerating expansion brings us right to the edge of our knowledge, to the final section and the biggest, most frustrating puzzle in cosmology today.
Here's the problem. We have two really good ways to measure how fast the universe is expanding. We can look at the past, using that afterglow from the Big Bang, the CMB, and use our best model of the universe to predict how fast it should be expanding today. Or we can just look out at the nearby universe, at stars and exploding supernovae, and measure the expansion rate directly. And here's the thing, they don't agree. The measurement from today is consistently 5 to 9% faster than the prediction from the past.
This disagreement, which scientists call the Hubble tension, is a genuine crisis. It means one of two things. Either one or both of our measurements are somehow subtly wrong, or, and this is the exciting part, our standard model of the universe, the one that's worked so well for decades, is actually missing something fundamental. So the question that keeps cosmologists up at night is, are we just on the cusp of refining our old theory? Or are we about to discover entirely new physics that will once again change everything we think we know about our cosmic origins?